In a previous lesson about matrix arithmetic and operations, we learned that we cannot divide by a matrix. Instead, we have to multiply by the inverse of the matrix. This lesson will be about how to get the inverse of a matrix. For a generic 2x2 matrix of the form A equals ABCD, the inverse is denoted by A raised to the power of minus 1, and is calculated as 1 over the determinant of A multiplied by the adjugate of A. As a side note, the adjugate may also be called the classical adjoint or adjunct matrix of A. The determinant for a 2x2 matrix is AD minus BC, and the adjugate, we interchange the positions of A and D, and then put a negative sign on B and also a negative sign on C. If we were to multiply the 1 over determinant into the matrix, this is the result that we would get. This middle formula is the one that I memorized to invert 2x2 matrices. Also keep in mind, when we invert an inverse, we get back the original matrix. Suppose A is 1, 2, 3, 4, and we want to find the inverse of this matrix. 1 over det A, the determinant is AD minus BC, 1 times 4 minus 2 times 3. Then the adjugate, we interchange the positions of A and D, flip the positions of 1 and 4. Then negative B, negative C, which means negative 2, negative 3. And we simplify everything. Det A is negative 2, 1 over det A is 1 over negative 2, and then multiply that through the adjugate. And simplifying those fractions, the inverse of A is negative 2, 1, 3 over 2, and 1 over negative 2. Let's do a more complicated example. Matrix M is cos theta, negative sine theta, and cos theta. Using the formula to invert 2x2 matrix, 1 over det M being AD minus BC, cos theta times cos theta minus negative sine theta times sine theta, and then the adjugate, we flip the position cos theta with cos theta. So I guess in this case, it doesn't look like we changed anything. And then negative B, negative C, we have a negative sine theta, which becomes a positive sine theta, and then negative sine theta. Simplifying the determinant, we have cos squared minus a negative sine squared. And we notice this as the Pythagorean identity. Cos squared plus sine squared equals 1. Determinant is 1, and 1 over 1 is just 1. Effectively, the inverse of M is just the adjugate of M, cos theta, sine theta, negative sine theta, cos theta. To invert matrices of 3x3 in higher dimensions, we follow a similar formula, 1 over det A multiplied by the adjugate of A. But in this case, the adjugate is much more complicated than a 2x2 adjugate. For 3x3 in higher dimensions, the adjugate is the transpose of the cofactor matrix. Using this formula is one way of getting the inverse of a 3x3 or higher matrix. A different way of matrix inversion is by augmenting the matrix we want to invert, let's call it A, to the identity matrix, and then row reducing so that we have I where A used to be, and on the other side, that used to be I is now A inverse. Let's use both ways to invert matrix B. First, we will use the formula 1 over det B multiplied by the adjugate of B, and then we will use the other way by augmenting to the identity and row reducing. In the cofactor matrix C, each element is going to be a determinant that we get when we cross off a row or column of matrix B. Starting at the 2, we cross off the row and column that has the 2, and then get the determinant of what's left. 2 minus 2, 5 and 0. For 3, we do something similar, cross off the row and column that has the 3, and then get the determinant of what's left. 0, negative 2, 6, 0, and so on for all the elements of matrix B. And then apply the plus and minus signs in an alternating pattern. Remember that the top left corner has to be a plus. Computing these determinants, we have AD minus BC. 2 times 0 minus negative 2 times 5, 10. And then next one, 0 times 0 minus a negative 2 times 6. Positive 12, but we have the negative associated with that position, so it's negative 12. And we continue for the remaining cofactors. And then we transpose the cofactor matrix C to get the adjugate of B. To transpose a matrix, all the rows become columns and all the columns become rows. For example, the first column, 10, negative 5, negative 4, becomes the first row, 10, -5, -4, and so on for other rows and columns. Now that we have adjugate of b, we get the determinant of b. Cofactor expansion along a row or column that has the most zeros. I just picked row 2. There are other rows and columns that also have 1 0. Also, remember to apply those alternating plus and minus signs when doing cofactor expansion. The first part is just 0, and then we move on to the 2, cross off the row and column that has the 2, and then take the determinant of that. 2 times 0 minus a -1 times 6. And then -2. But then there's that negative associated with that position, so it's a -2. Cross off the row and column that has the -2 and then get the determinant of that. 2 times 5 minus 3 times 6. Simplifying, the determinant of b is -4. Now we put everything together. 1 over det b, adjugate b. 1 over det b is 1 over -4, and then we put in our adjugate b. Multiplying 1 over -4 into adjugate of b, we have this answer as the inverse of b. A totally different way of inverting a matrix is by augmenting the matrix of interest with the identity, and then row reducing so that the original matrix turns into the identity. On the other side that used to be the identity is going to be the inverse that we want to find. Also, there are multiple ways of doing row reduction. What I'm showing is just one way that I happen to think of. You probably have another method of doing row reduction that works just as well. The first thing I notice is the 2 and the 6. If I multiply that 2 by 3, I can subtract with the 6 to get a 0. 3 times row 1 minus row 3. Comparing the 4 and the 2, if we multiply that 2 by 2, then we can subtract 4 with that 2. Row 1 minus 2 row 2. That -2 can be turned into a 0 using the 1. Row 2 plus 2 row 1. If we multiply the 5 by 2, we can subtract 5 times 2 to get a 0. 2 row 3 minus 5 row 2. 2 can be made into a leading 1. Multiply row 2 by 1 over 2. That 12 can also be a leading 1. Multiply row 3 by 1 over 12. The fractions in row 3 can be simplified. We flip row 1 and row 3 so that we have the identity on the left side. And on the right side is b inverse. We can check our work. No matter which method we use, we should get the same b inverse. Here's a more sophisticated example, a 4 by 4 matrix. We can find the inverse by any method. Personally, I prefer to augment the matrix to the identity and in row reducing to get the inverse, rather than doing the 1 over det A adjugate of A. I just find trying to calculate all those cofactors, that's tough for me to organize. If I can just row reduce, I feel that I will less likely make mistakes. Augmenting matrix A to the identity. If we go 2 minus 2 times that 1, we can get a 0. Row 1 minus 2 row 2. We can get rid of that plus 2 by adding to the minus 2. Row 3 plus row 4. The minus 2 can cancel with that 1 if we multiply that 1 by 2. Row 3 plus 2 row 2. We can cancel the minus 2 using 1. Row 4 plus 2 row 1. We have a 1 there and 1 there we can subtract to get rid of one of those 1s. Row 4 minus row 2. There's a 2 and a 1 there. If we go 2 minus 1 times 2, then we can get rid of that 2 in row 3. Row 3 minus 2 row 4. The 4 and the -3 have a common multiple of 12. One's a plus, one's a minus. We can cancel them by adding. 4 row 4 plus 3 row 3. We can turn that 4 into a leading 1. 1 over 4 times row 3. We can also turn that 4 into a leading 1. 1 over 4 times row 4. Now that we have the identity where matrix A used to be, the other side of this augmented matrix, where the identity used to be, is the inverse of A. Now for something easier, the inverse of diagonal matrices. We simply reciprocate each entry along the main diagonal. Here we have pi, e, and phi along the main diagonal. Then the inverse of this matrix is going to be 1 over pi, 1 over e, 1 over phi along the main diagonal. For an even easier matrix to invert is the identity. Identity only has 1s along the main diagonal. If we take the reciprocal of 1, it's just 1 is 1 over 1. Therefore, the identity and the inverse of the identity are the same matrices. Here are some things to keep in mind. So far, we've only talked about the inverse of square matrices because only square matrices are invertible. Non-square matrices are not invertible. If a square matrix has a row or column of zeros, then we cannot invert that matrix. And it has to do with the determinant. The formula to find the inverse of any matrix is 1 over det A times the adjugate of A. So then, if we have a row or column of zeros, then det A is going to be 0. 1 over 0, we can't do that. Division by 0 is undefined. Therefore, a matrix is only invertible, we can find the inverse, if its determinant is non-zero. If the determinant happens to be 0, then we cannot find the inverse of that matrix. Now is a good place to talk about equivalent statements. These come up everywhere in linear algebra. How equivalent statements work is that if one applies, then all of these other statements apply. If one fails, then all of these other statements fail. Right now we only have 2 statements. But as we go along in linear algebra, we're going to add to this list of equivalent statements. The 2 most relevant statements for this lesson are det A doesn't equal to 0, A is invertible. These equivalent statements reiterate what we just saw with these remarks. Determinant is non-zero, we can invert the matrix. On the flip side, determinant is 0, we cannot invert the matrix.